in the previous video, we determined the wave function for the hydrogen atom in the ground state. And before we did that, we also just discussed a little bit about the solution that we found previously. Basically, this procedure, all of these formulas that you can see right here. So if you have already watched that, then just go ahead, because in this video, we're going to find the first excited state for the hydrogen atom. So what I'm going to determine here is going to be psi2, 0, 0, psi2, 1, plus and minus 1, and psi2, 1, 0. So that's what we will do in this video. So let's go straight in, because this will take a while. Now let's begin with state psi2, 0, 0. This means, because remember this wave function is a product of the radial and the angular part being the spherical harmonics. So this is going to be R2, 0. Remember, this is N, this is L, and the spherical harmonics in this case will just be 0, 0. Now, the spherical harmonics here, we actually saw this particular one in the previous video. So this we saw is just 1 divided by the square root of 4 pi. So I will not be calculating that again. If you don't know why this value is this value, then you have to go back to the previous video and see the calculation there. So what we have to do in this case is just going to determine R2, 0. So let's take now the formulas that we have, that we determined previously. Once again, if any of this seems strange to you, then make sure to go back and rewatch some of the videos where I derived all of these formulas. So let's see, what is this case for n equals 2, L equals 0? Well, R2, 0 will be 1 over R e to the minus R divided by 2a, because n is 2. Then we got R divided by 2a to the, well, L is 0, so it's still just to the first power, times this function v of R. Now, remember the formula for this, we found this recursive formula that gives us these polynomials v of rho. We will have to do the conversion between rho and R, rho being R divided by NA. In this case, n will be 2. And this was just series solution, right? J equals 0 to infinity of aj times rho to the jth power. So let us now see what is the maximum value for j that we can use. So j max, as we can see from here, it happens that is the j for which this is 0. So j max will be n minus L minus 1. N in this case is 2, L is 0. So we're going to get 2 minus 1. So in this case, actually, j max will be 1. In the previous case, when we saw the ground state, it was 0. So this means we have to take this recursive formula and put in first j equals 0 and then j equals 1 and see what we get. Well, spoiler, j equals 1 will be 0, so that will actually not be quite important, but it's always good to make sure that it's correct. Okay, so j equals 0 means that a1 is going to be 2 times j is 0 plus L, that is also 0, plus 1 minus n, which is 2. And this is going to be divided by 1 times j is 0, this is 0, so 1 times 2. So this 2 cancels out this one, and then we have 1, this is times a0. And then we get here just a minus 1, so we just get minus a0. And as you can see, a2 will just be a0, because this was the maximum value for j. So what is our solution going to be? Our polynomial in terms of rho, this will be a0, which is the first case. Once again, please don't forget to put a0 here. And then we get, this is times rho to the 0th power times a1 rho to the first power. But what is rho to the 0? Well, that is just 1, so we don't really have to write it. Then we get a0 minus, because what is a1? a1 is minus a0 times rho. But what is rho? Rho is just R divided by NA, and since n is 2, this is going to be R divided by 2n. And finally, we can factor out a0, so we get a0, 1 minus R divided by 2n. So this is going to be this function. Let's go back and plug it into what we had right here. So instead of this function here, VR, we are going to get a0, 1 minus, what was it again? I already forgot. It was 1 minus r divided by 2n. And well, we can still do some simplifications here. So this r right here will cancel out this one right here. And just to make this look better, we can put this a0 in front and divide it by 2a there. So this is going to be like this, 1 minus r divided by 2n. Okay, so this right here is the radial solution for this case. Now this is not normalized, so we need to normalize it just as we did in the previous video. So let me take it, go to the next page, and we can begin with the process of normalizing it. Now to normalize this, we have to once again say, well, 1, this is just going to be the integral of this thing squared. So that's going to be, there we go, 0 to infinity, because we're integrating over r, times this thing squared. So we get a0 squared divided by 4a squared e to the minus r divided by a, because it's double this. So this divided by 2 goes away. And then we have 1 minus r divided by 2n squared. And now comes something extremely important. As I said in the previous video, do not forget the r squared, because we are integrating in spherical coordinates. And this is just part of the integral. Remember, in the previous video, we did the whole thing. This thing is also multiplied by the integral over the angular part, and that is where there's this sine part that is missing. So this r squared is just because we're integrating over spherical coordinates. So, well, now let's put the constant outside. So we got a0 squared divided by 4. The a squared I will leave in for a reason that I will explain in a minute. And then we have this thing right here. We can expand it. That's just going to be 1 minus r divided by, well, what is, wait, this is not n, sorry, this is 2a. 2a. Sorry about that. So 1 divided by a, because it's twice this, plus r squared divided by 4a squared. And all of this is multiplied by r squared, so let's actually just change that right away. So instead of 1, we get r squared minus r cubed, and this here is r to the 4th power. R to the 4th power. Okay, and we still need this a squared in here, and this is the reason why I separated it, because now we multiply all of this by 1 over a squared. So this first part will be a squared, this will be a cubed, and this right here will be a to the 4th power. And this is multiplied by e minus r divided by a dr. And why did I do this? Well, because this sort of integral, which is actually of the same form that we have in the previous video, is going to be much easier to solve if we say, let's introduce a new variable, which will be z, and we will call it just r divided by a, because that is here, 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 and here. That's why I left. Obviously, you don't need to use this constant of integration, so the substitution, but it's really going to make it much easier, and the fact it's going to help you see a pattern that will help you not have to integrate this all that much. Okay, so if we take this to be z, then dz will just be dr divided by a, but we can multiply a, so that dr is just a times dz. So let's now put this into our expression. So we get a0 squared divided by 4, integral from 0 to infinity. The boundaries do not change in this case. Factor of z squared minus z cubed plus z to the 4th power divided by 4. All of this e minus z times a dz. Do not forget this a. That's also very important. I can't stress it enough. Please don't forget that it comes from this part here. Okay, so this is what we now have to solve. Let me take it to the next page. Okay, what do we do here? Well, this integral we'll have to solve by integrating by parts. Each one of these, so we have 3 integrals that we have to solve by integrating by parts. I will show you now a trick that you can use. And I will begin integrating this part right here. So I will integrate, I'm going to leave the constants, these ones outside. So we get integral from 0 to infinity of z to the 4th power divided by 4, but I can just write it up down here in the front, e to the minus z dz. And there's still this a factor, but I'm just going to write it outside of all these integrals. Okay, so this is what we want to integrate. So let's just naively say, okay, let's begin and say, well, u, since we're integrating by parts, will be z to the 4th power, du will be 4z cubed. And then we have dv, which is just e to the minus z dz, and v is going to be minus e to the minus z. So let's plug it into this integral. So we get 1/4 factor of, let's see, so this first part will be minus z to the 4th e to the minus z evaluated between 0 and infinity. But we saw that in the previous video, and you can see if we evaluate this at infinity, it will go to 0, and if we evaluate it at 0, it will also be 0. So this part right here is just 0. And then we got the second part, which is minus the integral of this times this. But we got a double minus, so we get plus integral from 0 to infinity of 4z cubed e to the minus z dz. And we can write this 4 outside, right here. Don't cancel it with this 1/4 just yet, because I want you to see a pattern here. So let's just leave it there. And now we can actually notice first that this is the same form that we had before, except the exponent came down, and now we have z to the 3rd. So let's apply integration by part one more time. So u is equal to z cubed, du is equal to 3z squared, dv is going to be just as before, e minus z dz, and v will be minus e to the minus z. So when we now solve this integral, we get, well, 1/4 times 4 times the first term is minus z cubed times e to the minus z. But that's just 0. Same thing as before, because when you evaluate it at infinity and 0, it will be 0 both times, so that's just 0. And then we get minus this times this. So we get minus minus, which is plus. So we just get integral from 0 to infinity of 3z squared e to the minus z dz. Oh, there's dz missing here, sorry. So we get 3z squared e to the minus z dz. And you can see, once again, all we accomplish with this is to make the exponent here smaller by 1, and we are multiplying by the exponent. So actually you can see that when you're solving this kind of integral, for every time that you have to solve it, you're just going to get 4 times the integral, and at the end you're just going to get 1. So basically, when you solve this again by parts, and you can do it by hand the first time, it's good that you do it, but we're just going to get that this, and the fact this is kind of what we solved in the previous video, we're just going to get, in this case, well, there's the 1/4 that was lingering already, times 4, which is from this first integral, times 3 from this integral, times 2 from this integral, times 1 from the next integral that we haven't written here. So our result will just be 4 factorial. So that's our result here. And similarly, this right here will just be 3 times 2 times 1. And this integral right here will be 2 times 1. So let's now take this to the next page and actually set those results in. If you want, you're free to integrate by parts, but as you can see, you have to integrate by parts 4 times here, 3 times here, 2 times here. So it's really tedious if you have to do it each time. So it is good to notice this pattern. So 1 is going to be a0 squared divided by 4. And then we're going to have, well, this right here is going to be 2 times 1 minus 3 times 2 plus 1/4 times 4 times 3 times 2. So what is this going to be? Well, the 1/4 cancel out the 4, and we have minus 3 times 2, and then this plus 3 times 2, so they cancel each other out. So we're just going to be left with this, and this 2 will cancel out some of the 4, so we just get this right here. So a0 squared will be 2 divided by a, which says a0 is the square root of 2 divided by a. So this is the result for this constant of integration. Now let's put everything together into our result. So this here was the expression that we had for the radial function. So the radial function was this. I brought some things that I didn't want to bring along. This was a 2a. I'm just going to write it again to clarify. That's not much clearer. 2a. Okay. Now, let's see. So here now we want to plug in a0. So a0 is just square root of 2 divided by a. So we get times 1 divided by 2a, e to the minus r divided by 2a, 1 minus r divided by 2a. And now let us write, instead of just the radial function, let's multiply it by the spherical harmonic so that this becomes the actual wave function that we're looking for. So we have to multiply this by y0, 0, which we already know is 1 divided by the square root of 4 pi. And now, well, this is already technically correct. We can now see, well, what can we solve here? What can we simplify? So what can we simplify? Well, we got psi 2, 0, 0. And then let's see, we're going to take this 4, square root of 4 will just be 2. And since we are dividing square root of 2 by 2, we can cancel this and just write this one as square root of 2. So we will get square root of 2 pi a, but including this a, we use this, and also I'm going to use red maybe. So these two parts are the ones that we just used. Then we still have this 1 divided by 2a and 1 minus r divided by 2a, e to the minus r divided by 2a. And this right here is the wave function for the state psi 2, 0, 0. And the energy will just be the energy of the first of this ground state divided by n squared. And since n is 2, this will be E1 divided by 4. And remember, E1 is going to be minus 13.6 electron volts. So you can just plug it into the calculator and see what it's going to be, 4, something, I guess. And that's the result. Now let's proceed and start looking at the next case. Will be 2, 1, 0. I guess you could go for 2, 1, 1 or 2, 1 minus 1. It's okay. Let's solve this. Now this will be R21, remember, N, L, M, do not forget that, times Y, and this time it's going to be 1, 0. Okay, and now we have to calculate this. Begin with whatever makes you happy. Let's go for R21. So R21, remember in our formula, will be 1 over R, e to the minus r divided by NA, but n is 2a. Then we got r divided by NA, n is 2, so 2a, to the L plus 1 power, so this is going to be squared, times this polynomial that we need to determine. How do we determine it? We need to go back and use the recursive formula right here. Let's do that immediately. What's our maximum j in this particular case? Well, we can determine it by seeing when this is going to be 0. So j max is going to be n minus L minus 1. N in this case is 2, n is 1, and well, minus 1. So the maximum j will be 0. Let's plug that in here. And actually, the fact that it's 0, you can immediately see you will only have the first term, because you will only have a 0, because a1, which is when you plug in j equals 0, is already 0, right? This part right here will be 0, so that's already going to be 0. So our function v of rho will just be a0 times rho to the 0th power, which is just a0. So in this case, obviously, it doesn't matter. You don't have to put rho in terms of r. So let's plug that in here. So we get a 0 multiplying here, and this r squared will cancel out the r that is in front. So let me actually write this a bit prettier, just saying a0r divided by 4a squared e to the minus r divided by 2a. Now we need to determine the constant of integration a0. Let's go to the next page and do that immediately. This means 1 is going to be equal to the integral over all of the possible values of this r, which is from 0 to infinity, and we need to make sure to take this value, the modulus of this value of this function squared. This is our r of 2, 1. So we get a0 squared divided by 4a squared squared times r squared e to the minus r divided by a, the 2 goes away because it's squared, times r squared dr. This r squared, once again, it comes from the fact that we're integrating in these spherical coordinates. So let's put these r's together. So we get r to the 4th power. And once again, let's separate the a. So we get 4 squared, and here we have divided by a to the 4th power. Why do I do this? Because once again, we are going to use the change of variables. Z is r divided by a, and dr is going to be a dz. Let's put this into the integral then, and we get integral from 0 to infinity, a0 squared 4 squared, which we can actually just take outside of the integral, z to the 4th power, e to the minus z, and then we get a dz. And you can actually see this integral right here, since all of these are just constants, is just z to the 4th power e to the minus z. And we already saw the value of this integral. So a squared divided by 4 squared a times this integral, which is just going to be 4 factorial, which is 4 times 3 times 2 times 1. And now we can simplify a little bit. This 4 cancels out the exponent here. This 4 and this 2 will cancel out, and you get a 2 down here. So the result in the end will be a0 squared a times 3 divided by 2. And from here, we can now find a0, because this has to be equal to 1. So a0 squared, let me just make sure we cancel that. Yes, okay. So a0 squared will be 2 divided by 3a, and a0 will just be the square root of that. Now we have determined a0. Let's proceed by finding the value for the spherical harmonic. So the spherical harmonic when L is 1 and M is 0. What was the shape of the spherical harmonics? Well, it was this monster right there. But don't worry, we will slay this monster. So I think I copied everything. Let's go here. I'm going to set this over here just as a quick reminder. Okay, so to find y10, we need to find these associated Legendre polynomials, and to find the associated Legendre polynomials, we need to find the regular Legendre polynomials, for which we need this. Now, what is our value of L? Our value of L this time is 1. So this means what is going to be the maximum value for A? Well, if L is equal to 1, for this to terminate, J will have to be equal to 1. That means we're only going to be dealing with the odd values for these coefficients. And L equals 1 is going to be, well, it means J1, and J1 means that the coefficient where it terminates is going to be A3. So the only coefficient that is not going to be 0 is going to be A1. This means that our Legendre polynomial will be A1 times x to the first power. Remember, this is a power series, that's why, and please don't forget to, and don't just write A1, right? So A1 times x to the first power, which is just x. And now to find the Legendre polynomial, we have to plug, and this is not of any L, this is of L equals 1. So the associated Legendre polynomial for L equals 1 and M equals 0 in terms of x will be 1 minus x squared, m is 0. So this right here, it's just going to be 0. This right here is the 0th derivative, which means don't take the derivative of this. So basically this once again will also be the same as our Legendre polynomial. So it's just going to be a1 times x. But what we have to use is not these Legendre polynomials in terms and associated in terms of x, but in terms of cosine. So what we'll have is that our associated Legendre in terms of cosine will be a1, and instead of x, of cosine theta, because we had used the change of variables back when we solved this differential equation. That's why we need to substitute back. And well, the exponential here is going to be this is going to be e to the 0th power, so it's just 1, and this epsilon that is there by convention, and as we said, it's 1 if m is greater or equal to 0, and it's going to be minus 1 to the mth power is m is greater or equal to 0. So since m is 0, it's just going to be 1. So the spherical harmonic 1, 0 will just be some constant, which we can keep a big A or A1. It's kind of redundant to have both of them, to be honest. Let's just keep big A since it's the one that we used in the previous video. So big A times this right here, cosine theta. Here I just absorbed these two constants together, and the exponential is 0. Now we need to determine the constant of integration here before we can just say we're finished. So let's do that. So let's integrate over all of this angular space, which means we're going to integrate from 0 to 2 pi d phi. We're going to integrate theta from 0 to pi, and well, here's going to be our function squared. I took this out because the function doesn't depend on phi. So we get a squared cosine squared theta times sine theta. This sine theta comes from the fact that we're integrating in spherical coordinates. Okay, now this first integral is trivial, it's just 2 pi. And this one right here might be a bit tricky if you don't see the trick. So what is the derivative of cosine? The derivative of cosine is going to be minus sine. So we can see here we have something that depends on cosine and something that depends on its derivative. So it might be logical to say, okay, let's try and see what happens if we say, okay, u is going to be cosine of theta, and du in that case is just going to be minus sine theta d theta. So we can now plug this in here. So we get 1 is going to be 2 pi integral. Well, what are the new limits of the integral? If theta is 0, u will be 1. And if theta is pi, u will be minus 1. Okay, don't forget to change the limits of the integral unless you are planning to change back into your original variables before applying the limits. Okay, and then we get a squared. Cosine squared is going to be u squared, and sine theta d theta is going to be minus du. Now this integral is going to be easy to solve. It's just integral from 1 to minus 1 of u squared. So that's just going to be u cubed, my tablet lagged, u cubed divided by 3, evaluated between 1 and minus 1. So let's evaluate it. We get minus 2 pi a. So when we evaluate this at minus 1, we get minus 1 divided by 3 minus evaluating this at 1. So we get 1/3, but it already had the minus sign in front. So the two minus signs can go out and cancel the minus sign that is up front. And we get 2 pi a. And well, and this is just going to be times 2/3. This is a squared, by the way. I don't know why I dropped the squared. Let's make sure. Yes. Okay. And well, this will be 4 pi a squared divided by 3. And here we can see then that a squared will be 3 divided by 4 pi. And thus a will be the square root of 3 divided by 4 pi. Now that we have found this value, we can plug it into our spherical harmonic right here, just to make sure that we don't forget that there's also a cosine here. 3 divided by 4 pi cosine theta is our spherical harmonic. let's plug all of this back into the formula for psi21. Let me see. Yeah, I was going to do it here. So let's see. Let's use psi21, 0. This is going to be the radial part times the angular part. This is the angular part. And let me now go look for the radial part. So the radial part, I didn't write it all together. It was this right here, and a0 is this. So we're going to get square root of 2 divided by 3a times r divided by 4a squared e to the minus r divided by 2a. So let's now take this here as well. And multiply it all together. Now let's see, what can we simplify? Well, there is this factor of square root of 3 that which we can simplify. And then what else do we have? Well, once again, the square root of 4, it's just going to be 2. And since we are multiplying by this square root of 2, we can just write it as a square root of 2 in the denominator. And with that, we get rid of those terms. And I think that's basically it. So let's write it all. So we're going to get 1 divided by the square root of 2 pi a times 1, or actually r divided by 4a squared times e to the minus r divided by 2a cosine theta. Okay, so there we go. This is the wave function for psi210, and we can see that it's going to have the same energy level, the same energy as psi200, because the energy does not depend on L and M, which is actually quite interesting. We don't know much about L and M just yet. We will see more about that when we are working with angular momentum. Let us now begin with the final two wave functions that we want to determine, which is psi211 and psi2 minus 1. Here we can see that actually some of the work has been already done, because any of these, for example, let's begin with psi211. This is just going to be the radial function of 2,1 times the spherical harmonic of 1,1. And the radial part we have already determined in the previous part. So all that we need to determine now is going to be psi11 and psi1 minus 1, in this case for the other wave function. Okay, so let's go back to our formula for the spherical harmonics, which is all of this. Okay, now let's go for our Legendre polynomials. That's where we begin. What is our value for L? Our value for L is 1 once again. And in fact, let us actually take a look at this, because our L here is in fact the same as before, and the Legendre polynomial depends only on L. So actually we already know what the Legendre polynomial is. We already found it. The Legendre polynomial, when L is equal to 1, is simply some constant times cosine theta. That's what we found before. Well, technically it's times x. The cosine theta is when we already applied it, but first we still have to see what happens in this step right here. So now let's go in here. So P1, 1, this time M is not 0. So we can't just say this is 1. So 1 minus x squared to the 1/2 power times the derivative, the first derivative of this polynomial, which is just a1x. So deriving that, we are going to get 1 minus x squared to the 1/2 power times the first derivative of this, but it's just a1x. So when you derive it, you just get a1. Now the final step is to write it in terms of cosine. So instead of x, we put a cosine in. So this is going to be equal to 1 minus cosine squared theta to the 1/2 power a1. But what is 1 minus cosine squared theta? That's just sine squared theta to the 1/2 power a1. And this is basically the square root. So we just get a1 sine theta. That's going to be the associated Legendre polynomial for L equal 1, M equals 1. And in fact, this here only depends on the absolute value of M. It doesn't really depend on just M itself. So this will be the same for P1 minus 1. So in fact, we're kind of doing the work double here. Double the work, no, half the work, sorry. So that's good. That's good. Doing less work is always good. Let's now go to the next page and see what the spherical harmonics are for this case. So this is going to be some constant of integration, which we can combine with our A1 times A1, which as I said we combine, so I'm not going to write it, times sine theta. And now comes a very important step. Before we didn't have to include it, this exponential right here, because M was 0, so it was just 1. This time M is equal to 1. So this will be e to the I phi. And then we have to take a look at this epsilon right here. So that epsilon, what is it going to be? It's going to be, as we said, just in case we need a reminder, this epsilon is going to be 1 if M is less or equal to 0, basically negative or 0. And it's going to be minus 1 to the mth power if M is greater or equal to 0. In this case, M is 1, so it's greater than 0, so it's minus 1 to the first power. So it's just minus 1. That's by convention. So let us just, here we were, yeah. So this is going to be multiplied by minus 1, so let's just put it in front. Okay, that's our spherical harmonic. We can actually just go ahead and construct the spherical harmonic for 1 minus 1, because in this case we're going to get the same associated Legendre polynomial as we saw, but the exponential will be minus I phi, because M is minus 1. And because it is minus 1, this time this condition will apply. So epsilon will be 1, because M is negative. So it will be just what we have right there. Now we need to normalize both of these. And in fact, we can see that we won't have to do all that much work. Now let's normalize it. So we get 1 has to be equal, let's begin with this one, to the integral from 0 to 2 pi, integral from 0 to pi of a squared. This minus sign will cancel out because we are squaring this, basically. We're taking its complex conjugate and multiplying by just this function right here. And then we have this e to the minus I phi sine squared theta e to the I phi. So the exponentials will cancel out as well. And in fact, we can see now that if we do the same procedure for this other harmonic, we will see that we get the same thing. Because the difference was in the minus sign here, which cancelled out, became positive, and in the exponential, which also just cancelled out. Okay, so now we need to multiply this by another sine theta, because we're integrating over spherical coordinates, and d theta. How can we solve this? What I would do is say, okay, let's remember that sine squared theta is going to be 1 minus cosine square of theta. Let's plug it in here. So we get 1 minus cosine squared of theta. Let's multiply through. Well, we can, oh, by the way, I missed the d phi. We can just solve the phi integral right away. It's going to be 2 pi. We can write the a squared outside. Integral from 0 to pi. And now we're going to get two parts. So first 1 times sine theta. So it's just sine theta. And then we have minus, and take a look at this, sine theta cosine squared theta, and all of this d theta. Now this part right here may be familiar. We actually just solved that. I'm gonna try and see where the integral was. It was right here, right? It was cosine squared sine theta, and the result for this integral was that it's minus 2/3. So let's just plug in. I mean, there's no reason to do the integral again. So this right here is going to be minus 2/3, but there is already a minus in there. So let's see, we got 1 is equal to 2 pi a squared. And then, well, we still have to integrate the sign, but that is easy. And in fact, we already solved that before. I don't know if it was in this video, I think it was the previous one. So that's going to be minus cosine theta evaluated between 0 and pi. But what is that? That is just going to be, well, at pi, it's going to be minus 1, but we have a minus sign in front, so we get 1. And then at 0, it's going to be 1, but we have minus, and then another minus, because when you evaluate by this, you have to include a minus. So we get plus 1. So basically, this part is just 2. So we get 2, and then we have this part right here. So we get 2 minus, let me make sure that this sign is correct. It looks weird right now. Let's see. So the value for this integral, let's see, du minus, yeah, we took, yeah, it's 2/3 because I had put the minus sign outside. It is 2/3, not minus 2/3. That's why this was looking weird. So it is plus 2/3, and then it's going to be minus 2/3 because of this minus sign right here. And well, so 2 pi a squared. This 2 right here, we can write it as 6 divided by 3 minus 2 divided by 3, which is going to be 4 divided by 3. And multiplying by this 2, we're going to have 8 pi a squared divided by 3. This has to be equal to 1, so a will just be 3 divided by 8 pi, and take the square root of all of that. Okay, so this right here is the normalization constant for both of these cases. So let me write it all together. So y11 is going to be minus square root of 3 divided by a pi sine theta e to the I phi, and I1 minus 1 will be positive 3 divided by 8 pi sine theta e to the minus I phi. Okay, now we are almost ready. We only need to combine this with the radial part. So 211, this will be the radial function. Let me go looking for it. R21, let's see, where is the final result? Because here it's without the A0, I think it was right here. Yeah, this right here is it. Okay. I'm going to get rid of these lines. They were from before, so it's square root of 2 divided by 3a. And this has to be multiplied by the spherical harmonic right here. So it's going to be, well, the minus sign, let's just leave it in front. Square root of 3 divided by 8 pi sine theta e to the I phi. How can we simplify this? Well, this 3 cancels out this. This square root of 8 is basically square root of 2 times 4. And the 2 will cancel out this one right here. And the 4 is just 2. So when we do that, let's see, we're going to get 1 divided by the square root of a pi times r divided by, and then we have 4 times 2. So that's going to be 8a squared. So let's see, I consider this, that, the 8, this, that, the r, that. Okay, so then we have a e to the minus r to a sine theta e to the I phi. And the case for psi 2, 1, minus 1, it's actually going to be basically the same. Oh, by the way, I left the minus sign out, except for the fact that it's not going to have this minus sign, and this sign will be negative. So it's going to be 1 divided by, well, I'm going to write it pi a. I like it better like that, but it doesn't matter. Times r8a squared e to the minus r divided by 2a sine theta e to the minus I phi. And once again, these will have the same energy levels as what we saw previously, because n is still just 2. So well, you are welcome to continue to do more of these wave functions if you want to just get the feel of this, but I'm going to leave it at this for now because, well, I hope this gives you a sense of where it's going and how you can determine these wave functions and how you can normalize them. So I hope you enjoyed these videos. I will see you in the next one.